Case number 3, N1 and N2 are separated by exactly 1. So it could be the case that N2 is equal to N1 plus 1 or N1 equals N2 plus 1. But the two cases are quite similar. Of course, the result will be different, but how you solve it is quite similar. So I'm just going to solve one of these cases where N2 equals N1 plus 1. In this case, Wn1, look at this. It's Yn1 plus Yn1 minus 1 over 2. And when you look at Wn2, it's Yn2 plus Yn2 minus 1 over 2. When you put in this here, you have y of n1 plus 1 and n1 plus 1 minus 1. Here you have y of n1 divided by 2. Now observe, Wn1 has a term of yn1 in it, and Wn2 has a term of yn1 in it. That means Wn1 and Wn2 are not independent. Okay, this makes matters complicated. So how am I going to write this joint probability? This is Wn1, this is Wn2. Okay, but you see they have this common term. What you can do is condition on the common term to get rid of it, right? Apply the law of total probability, condition this joint probability on the value of yn1, and I know that y of n1 is a Gaussian. It's a zero mean and variance sigma square Gaussian. So this conditional probability multiplied by the PDF of yn1, which is Gaussian, integrate over the entire real line. And now when you plug in this value into these two expressions, what you get is y of n1 minus, well, since this is u, y of n1 minus 1 is less than or equal to 2 times w1 minus u. Similarly here, y of n1 plus 1 is less than or equal to 2 times w2 minus, this is u. Okay? Now, you see, I have y of n1 minus 1 in this joint probability and y of n1 plus 1. Now they are independent because y of n1 minus 1 and y of n1 plus 1 are observed at different time instants, and I know y to be IID, and therefore they are independent, and I can separate them. One of them is this CDF, because y of n is a Gaussian, and the other one can be expressed as this CDF, and the PDF of yn1 can be expressed in this way. So if you compute this integral, well, you have to do it numerically, of course, but you can obtain the joint distribution of Wn1, Wn2 when n2 equals n1 plus 1. You can do the same for n1 equals n2 plus 1, but you see when there is overlap, it becomes complicated due to not being independent. There is an alternative way. Since we would like to compute the joint distribution, we can look at Wn1 and Wn2 as a random vector. And we know that both of them are linear combinations of IID Gaussians. When Gaussians are IID, they are obviously jointly Gaussian. Therefore, I can write W vector as this linear combination in terms of the outcomes of yn. When you have this linear combination, of course, we know that we can write the expected value in this way. Since all the means of these observations, y sub n's, y of n's are 0, the means of w will also be 0. And therefore, the expected value of Wn1, Wn2 is 0. Okay. How about the covariance matrix? Well, this should be W, KW. And this is the transformation matrix, and this is the transformation matrix transposed. And this here is the covariance matrix of this. How do I write this? Because I know they are IID. They have the same variance over the diagonal. And off diagonals are 0 because they are independent. Okay, if you arrange this, what you get is this matrix, which is the covariance matrix of this W vector. Okay, now I have the means which are 0, and I have the covariance matrix, so I can write the joint PDF, and then I can compute this joint probability using this double integral.